Let's go ahead and get started. Hello, everybody. My name is Brandon Miner. I'm CEO and co-founder of Tangram Vision, and today is another MetriCal office hour. So this is a relatively new event, I guess, recurring event that Tangram is holding. So every Tuesday, I or another part of the Tangram team will get online and either go through a demo of MetriCal, the latest and greatest, and go through a data set that we've collected and would like to show you, or just have open office hours. So if you're interested in talking to us one-on-one, getting a better feel for calibration in your own pipeline, or wondering what Tangram can do for you, either with MetriCal, with our auto calibration efforts, or otherwise, that's a great opportunity to do so. So this week obviously is a MetriCal update, but next week will be office hours. So if that is interesting to you, go online to tangramvision.com/ I think it's Tangram office hours. It'll be in the slide deck, and reserve a spot. But with that, let's get into it. I'll share my screen really quickly, and we can start going through some of this fun stuff. So to start with, I have a few announcements and slides. So let's check it out. MetriCal office hours. July 29th, 2025. Here we are. So obviously, first and foremost, what I kind of just covered. Tangram office hours are every Tuesday, starting at 2 p.m. Central Time. I've already had some asks for different times, specifically for Europe and Asian users of the product. But right now, for now, it's just 2 p.m. Central Time. And like I said, every week will either be a MetriCal demo, every other week is open office hours. So depending on what you're interested in, go online, sign up for the office hours or the next demo, and jump on in. So here today, MetriCal demo, we're talking about MetriCal, which is Tangram Vision's multimodal calibration suite for production lines, maintenance, things where you need to understand ground truth practically in your calibration before you deploy. Last week, I would have said MetriCal has 3 modalities. It supports cameras, LiDAR, and IMU. But this week, I am excited to announce, and the dataset we'll be going over today, has local navigation systems. So MetriCal now has 4 different sensor modalities, sensing modalities that it can calibrate. Of course, we can take N number of cameras, LiDAR, and IMU. That is still true. But now we can also digest odometry messages and align odometry with any of these sensor modalities. I guess I'll caveat by saying we do require cameras right now. So it's camera to nav, and we will also align LiDAR and IMU if those are available. But at the bare minimum, you should be able to understand camera to chassis calibration, for instance. We're also working on things like hand-eye and hand or eye-to-hand calibration for robotic arms, which you can massage into something like an odometry, right? So really exciting. This has been a long time ask from many customers, and now we're excited to provide it. Of course, it's going to need a little bit of rigorous testing. The other 3 modalities have been in production for near 2 or 3 years with some customers, and this is just brand new. So if you are interested, we encourage you to pick it up, test it out. I'll be going through a demo of local navigation systems today, kind of showing what we can do today. And yeah, just message us if you have any other requirements as far as that goes. So MetriCal now has 4 modalities, really exciting. If you through the course of this demo or through the course of you just looking online and trying MetriCal out yourself, if you see something that if your product needs something that MetriCal does not provide, but could be wrapped into the MetriCal suite, just let us know. We have professional services we offer. So this isn't just augmenting MetriCal for your use case. It could also be setting up an entire calibration pipeline for your production line, right? We have experience with that. Setting up fiducials, setting up standard operating procedures, all of these things we have experience with and are available to help with. Just email us and let us know. That email, info@tangramvision.com, will be at the end of these slides. So if you can't catch it, don't worry, we'll bring it back up. So with all that being said, let's dive into the demo. There's a lot to cover today. Today we're going to go over local navigation systems. So this is MetriCal's brand new modality, and we have updated our documentation to lead you through kind of what a platonic data set might look like for local navigation systems. So this would be first and foremost a camera and a source of odometry. And that odometry is going to be written into MCAP's, odometry formation or Ross's odometry message format. And we'll get into the specifics of how we read that later on. But if you'd like to follow along, the data set I'm going through is actually available on our documentation. You can download it yourself, play around with it. MetriCal is also downloadable for free. You don't need a license. The only thing you won't get is the calibration numbers themselves. So MetriCal will still report all metrics, all errors, everything that you could want to evaluate the quality of your calibration. But without a license, it won't give you the calibration numbers that you can input into an algorithm, right? If you are interested in trying it, go to docs.tangramvision.com and go through the installation procedure. It's available as a Docker and as a .debian file, .deb. So if you're native to Ubuntu, you can just run it straight from your computer. And that's what I will be doing today for the latest version, 14.1.2. So with that being said, let's dive into the demo. I'll stop sharing this screen and share better screen right here. Share this guy. All right. Excellent. So now we are in the land of code. If you've never seen a MetriCal script, MetriCal, in order to calibrate, MetriCal has a ton of methods. We're only going to go over 2 or 3 of them today, but really MetriCal is designed for pipelining data through so that you can basically script your entire calibration process. A lot of our users literally automate their entire calibration procedure end to end. Often this will cut down their calibration procedure by hours. If that is not the case and you are a MetriCal user, we encourage you to contact us so that we can help you get those time savings. Because really that's where MetriCal's strength comes in. Accuracy is kind of table stakes in this world. What we really want to provide is ease of use and time savings throughout the lifetime of your system, right? So with all that being said, we've scripted this entire thing. It really shouldn't take too long other than data ingress, which we'll get into. But here's our bash script to run MetriCal. So I have the demo dataset downloaded, demo LNS. It is an MCAP. We prefer MCAPs. If you've never seen an MCAP, check out the format online. It is now the default output for ROS2 recording, I believe. And if you have a ROS1 bag or a set of folders, it can be massaged into an MCAP pretty easily, which is why we prefer it. We are going to output our results into a JSON called results LNS. This JSON's pretty meaty. It will have not just your results, but also all of the metrics and errors you would need to evaluate that calibration. We're going to log a results, I guess this would be a report more. We're going to log a report to a report HTML. This is going to massage the results into a human readable format where you can basically just save off a web page and see how this calibration is done. When we run MetriCal, this report will actually be output to the console And that console output is mirrored in this HTML. Our object space, OBJ here, defines the things we're looking for to inform our calibration. So in most instances, this is going to be a target or a retroreflective circle in the case of calibrating LiDAR. Things like Truco boards, April grids, dot boards. We take in a few different types of fiducial or target to identify exactly what we're looking for. We don't need these things to be surveyed. That's one of MetriCal's powers, really big strengths, is that you can use as many boards as you'd like. You just need to tell us what they look like so that we can do the optimization ourselves. So let's look into that, what this object space actually looks like. It's a little convoluted. You'll rarely have to make one of these yourself, but if you do, there are a few keys that you have to keep in mind. First is the object spaces key. Every target we're going to look for has a unique identifier, a UUID. So here we have one target, two targets that we'll be looking out for. Our descriptor is just a sense of how bent our boards are. So what is the variance we can expect point to point in a board? Right now, this is set to 1e -6, which is about a millimeter deviation in X, Y, and Z. You see X, Y, and Z. This is about the maximum that we recommend. If you have a board that's more warped than that, we would recommend you just change your board. And this will actually be an error metric that we output at the end of the report. You can always ignore that error metric. We allow that. But, for these production line calibrations, you really should be using something a little bit more rigid. You can see I have a board printed here. It's quite big. It's for camera LiDAR. Ideally, I would have, oh, not ideally, when I do calibrate a LiDAR with this, I would need to put retroreflective tape around this so that we can register both modalities. But you can see, even though it has a little bit of bend, 1e -6 is still going to capture this. It's not a lot at all. It would be if I actually, torqued this quite a bit, that we would have worries. So even with, the maximum variance, you can get away with a lot. All that being said, descriptor just tells you how warped these things are. Detector is what we're looking for. In this case, in this data set, we have two marker boards, nearly identical parameters. This one is just a little bit bigger. They're made with the Aruka 5x5 target, and they're offset by 100. So you can see this has sequential ID starting at 0. This has sequential ID targets starting at 100. And that's it. That's our entire thing. There are a couple other little required keys, but you really don't need them because we're just looking for two targets. And as far as configuration goes, that is the most we will need to do. We do not need to understand the CAD of your system. We don't need to understand the parameters of your previous calibrations. If you have ground truth, all of that is derived for you. We just need to look at what we're doing, or we just need to find what we're looking for. And then MetriCal does the rest, right? So really, this is a process of one and done. And I guess the last thing to cover, and I'll actually start this in the background. The last thing to cover is this initplex. So MetriCal has two phases to an initialization or to a calibration. The first is initialization of that calibration, and the second is the calibration itself. A plex refers to a calibration at a state and time. So you can think of like multiplexing is bringing in a bunch of sensor systems at the same time. Plex is kind of a play on that and just capturing that sensor state at a certain time. So what we're going to do, oh, thank you, is manufacture what we think of is the best guess at our calibration at that state and time. And then with the calibrate, init will have our best guess, and then the calibrate will massage that best guess into something that actually fits our data, right? The -m going through MetriCal init here. Dash Y says regenerate our initialization every time. If you already had an initialized plex living at initplex.json, it will just skip this step saying, hey, you've already initialized, you're good to go. Otherwise, we'll need to do it again. And dash Y just says force that. Dash M is when we actually assign our models. So this data set has certain set of cameras. I think it's 4 cameras, and every one of them has the word camera in the topic. So with this ROSBAG or with this MCAP, I've said everything that has camera as a glob, star camera star, I'm going to assign the extended unified camera model, EUCM. Now, EUCM only is one of the 10 camera models that MetriCal provides. We have from narrow to omnidirectional camera models, whatever you need. EUCM is just one of the more general for a wide field of view lens. And then we have this ODOM topic. Anything with ODOM, we're going to mark as a local navigation system. That's just saying an odometry is a local navigation system, treat it as an alignment. And that's it. So we're using that data set, our MCAP, and outputting the initialized plex here. That was a lot of words for something that, doesn't take a lot to do. We're just looking through the first couple of observations saying, what's my best guess of this calibration? What do I need to find? What are the spatial extrinsics that are important to me? We're going to put all that into calibrate mode. And so let's go over the arguments that I've passed here. Dash R is render this to rerun. I opened this, here we go. Here in this terminal, you can see I've started rerun with a memory limit of 4 GB so that it doesn't overwhelm my computer. And I've actually started running detections in the background while I explain everything. Generally, running rerun will extend your detection time by quite a bit because you're also rendering everything you detect. But really, data I/O is the biggest time suck in MetriCal. This is not to say that you shouldn't gather enough data to get a good calibration. Of course, gather as much data as you need, but understand that the more data you take, the longer it will take to bring that data in. The bundle adjustment itself, the calibration itself, is actually quite quick and is one of MetriCal's strengths again. So while that churns, let's go over. Dash Y is saying redetect everything every time. One of Calibrate's one of the cool things about Calibrate mode is that it can actually save the detections from a data set. So instead of having to detect everything every time you run a data set, it's just going to save the detections off in a JSON. And then if you wanted to tweak parameters, say I wanted to run this again, but instead of doing EUCM, I wanted to evaluate all of my cameras with rad-tan, OpenCV's default. I could do that. I could rerun initialization with dash Y and say, I want to do all of my cameras now rad-tan instead of EUCM. And I want to use those previous detections and just calibrate again. Get rid of dash Y, use those detections from last run, and you've drastically reduced the time it takes to calibrate. Dash O is saying we're saving our output to a certain file. This is results LNS JSON. Dash dash report path gives the report HTML. Report HTML will not be saved by default. You have to provide the report path, whereas an output would always be saved regardless of whether you provide dash O or not. And then the default arguments are what data am I churning out, or what data am I churning through? What was my best guess for the plex? What models did I assign, basically? And then what objects am I looking for, dash OBJ. So again, a lot of words for something that should take, very little kind of thought, I guess. So while this churns, you can see we're going through our data now. And let me make this a little smaller. Let's see. Go over here. Here we go. Boop. Hey, there we go. So let's look over this output. as I ran my script, camera LNS, we first did the initialization of the Plex. You can see it assigned everything that had camera to EUCM model, and the odometry message was assigned local navigation system, which does not have an intrinsic value. We're just taking extrinsic because it's odometry, right? It's motion. And now we're going through our detections slowly but surely because I'm also rendering them off to the side, and you're going to see that in a little bit. And once these detections are through, we're going to go immediately into a pre-metric evaluation and then adjustment. So let me shut this down, or let me share another screen. Let me show you what rerun's doing in the other side. And we can get into that. Check this out. So while I've been talking, we've been processing the detections for this data set. And here we are. So these are my 4 images. And as we go through, you can see a few things that I'll highlight now. So if you zoom into this, this is the 4th image compressed. You can see we're detecting both boards. Remember, we described 2 objects in our JSON. We're detecting both of them at the same time. And so here are the detections for object 24E6, blah, blah, blah. And then our detections in this board as well. Notice that the second one is a circle target. It's actually we've designed to do camera LiDAR. There is no LiDAR in this data set, but it doesn't matter, right? This camera board can still be used as a camera fiducial, no matter if there's a LiDAR or not, right? So this is why we generally create LiDAR detectors, this is circle, with a camera feature inside, because even if you're not doing LiDAR, you just get a free fiducial, right? So this is a easy gut check for our features, and we can even track individual features if we really wanted to. This data set, by the way, is taken using one of NVIDIA's mobile robotics platforms. They were sweet enough to let us borrow. So if you are recording on an NVIDIA platform, you should be able to process your data straight away. You know, just record an MCAP and it's ready to process. We have the ability to process the compressed video that records, even though it's in kind of a strange format. We've embedded that into MetriCal, and you should be able to generate it. You can see the team lounging around, and by lounging, I mean coding incredibly hard at a retreat. Let's take a look at the timeline, because this is also important and will be reflected in the report that we get later on. So this timeline is showing you not just when you get detections, but the number of detections. It's kind of the thickness of this line, right? So the thicker the line, the more detections, the more features that we're getting at that moment. And if we zoom in here, we can see, for instance, back fisheye camera drops off immediately after that moment. And if we screen out, we can see we're getting basically all cameras at the same time now, right? We've worked to mirror this detector in the MetriCal report, so you won't have to have rerun running every time. You'll be able to see most of this data just in the report straight up. And when that's generated, we'll be able to check that out later. But yeah, so the -R is just a really good gut check to see, one, if your object space is correct. First and foremost, that is where most errors start when you're first running MetriCal, is just getting your object space incorrect. And then second off, are the detections coming through that you would expect? Our detectors, we've worked really hard on our detectors for robustness. Just because the numbers are flickering up here doesn't mean the detections are jumping out. It's just an artifact of rerun. You can see these are actually pretty solid. So if you do see that your detections are failing when you're running MetriCal, please let us know. We've actually just done an overhaul of our April grid detector, for instance, due to user feedback in the field during like some productions that were taking 20 minutes of data and only 2 minutes of data were getting processed. That's something you should flag with us immediately because that's the kind of stuff we live to improve. All that being said, our visual detectors should be solid. And really, we're moving on as a company to probably working on detectors that, are fiducial-less. And that's, while we're generating this data, I'm going to put out a shout out to our auto calibration work. So if you are a company who, either has a calibration procedure in-house but doesn't have one in deployment, or needs a calibration procedure, something like MetriCal, and would like to extend that work into, you know, um, understanding your calibration and deployment, let us know, because as a company, Tangram has been awarded a phase 2 from NASA specifically to develop auto calibration on the moon. Right. And so what that really means is we're developing auto calibration in an environment where there's no operator and there are challenging, there's challenging lighting and landmark conditions. So regardless of whether you live or whether you operate in a challenging environment, if you are interested in AutoCal and would like to be a design partner, please let us know. Please reach out because what we're really looking for is similar to MetriCal, where we've vetted our algorithms over and over again on all sorts of robotic platforms and environments. We want to do the same thing with AutoCal. The more data we can get, the more users we can get early on, the better our solution will be in the field, the more capable we'll be for a actual mission to the moon or another extraterrestrial environment, right? So all that being said, if you're interested, let us know. That'd be really exciting. Again, that email is info@tangramvision.com. And if you want more information, we've recently written a blog post on the whole SBIR and our auto calibration mission that you can check out. Cool. So let's see, we have about 13, 26, 18, 16. We have about 5 minutes left. Rendering's kind of a bummer in this way. It does take much longer to generate these things. So I'm going to stop sharing, and while we go through those detections, let's discuss a little bit more about LNS and those requirements, since that's brand new. Dun, dun, dun. MetriCal share. So if you open up docs.metrical.com, you'll see our updated documentation for version 14.1. As a side, you can always see, well, if we've updated it, you can see the latest from our release candidate branch. We sometimes update the documentation in the dev latest section here. But by default, you'll go to our latest stable release, which is right now 14.1. If we go through the change logs for that, you can see plenty has changed for the better. Again, due to customer feedback and different operating environments, always improving the robustness of MetriCal. But really, the biggest change was introduction of local navigation systems, which we're going over today. This page is kind of bare, but that's because there are no local navigation system models. Local navigation systems are, by definition, just odometry. So we take odometry messages. If you're using ROS1 encodings, this would be a nav message odometry. If you're using ROS2, this is nav messages odometry. There is no protobuf right now, but with IMU and odometry, if you have something custom, it can usually be massaged into one of these two formats. Not a huge deal. With that, I will say that we don't currently accept odometry from, I don't believe we accept odometry from ROS1 bags or folders. In the future, we really are going to be centralizing on MCAP. And though you can use ROS1 bags and folders right now, 14.1 is certainly doable. we're going to be deprecating those in the future, in the near future, and providing our own converters between these formats to MCAP so that you won't have lost any functionality with MetriCal. You'll just have to have an extra conversion step. We do have some customers using ROS1 and folders, and it is an annoyance, I realize, but there are a few things that make this make sense for us as a calibration company. One, MCAPs are, becoming a pretty standard format, and they're very flexible. We're actually a release coming soon to MetriCal will actually change our outputs from JSON into an MCAP, so that you can render results and compress that data much more easily. So we're going to be soon centralizing on MCAP for input and output. Anyway, all that is to say, if you're still on ROS1 or folders, it's okay today, but realize that in the very near future, we're going to be asking you to convert. And we're giving those methods to convert. For LNS, going back to LNS, we're strictly odometry. Local navigation systems only have one model, which is LNS. Give it the keyword LNS when assigning the model in MetriCal, which is what we did in init mode. And then if we go to our local navigation system run through, you can see the data set that we're working with today. Note that you do need a camera right now. A camera is present. And you can actually purchase targets from us now. So we have an online store for targets. If you need a camera calibration box or something for camera LiDAR, go here. It's a pretty easy thing. But we also give you the targets that you can make your own. So the MetriCal pre-made targets repository right here is a whole Git repository of targets for MetriCal, either LiDAR or no LiDAR, and you can get them in all sorts of shapes and sizes. So we provide both April grid, marker grid, dense, sparse, and standard, and we'll give you both the object space file and the PDF needed to print that. So yeah, and here's our script running the example data set. Pretty easy. Let's go back to that, by the way, because I think it's just finished up. Dun, dun, dun. Share. All right, check it out. So now we're in the throes of calibration. It's moving really fast. I told you data IO is the longest part here. But let's go back up and see what we did beforehand. So we finished our data intake. It took longer because we were rendering, of course. But once we did that, MetriCal provided a bunch of metrics that we could use to evaluate just the data, not even the quality of the calibration, just the data for the calibration, right? You can see, first and foremost, MetriCal has motion thresholds. It actually has a motion filter that we run for cameras in LNS or cameras in LiDAR. If you shift over 1 pixel per observation, we're going to consider that camera moving. And by 1 pixel, I mean 1 pixel of detection. So if the detector moved at least 1 pixel per observation between observations, we consider that frame moving. And if the frame is moving, we'll filter it out. We'll get to that in a bit. So once we filter out our data, which we can see here, all of our process observation count, we had 6,405 read, 3,670 of those from this observation or from this component had detections. 3,402 of those fit our quality metrics, which are number of detections, angle of detections, blah, 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 a couple of filters. And then we only saved 150 after motion. So if we increase that motion threshold, which we can do from the arguments, we can get more data. That can be 2, 5. You can turn it off entirely. But right now we set it to the default and we only got 150 observations, which is totally fine. We can get a good calibration from that. Here's the coverage of our features in this data set. You can see that the bottom of the cameras, if we're thinking of this as a binned image, the bottom of the camera's got very few features, but that's something we can improve on a subsequent calibration capture. right? And then here's that timeline of detections that we provide for you. You can generally see if you don't have this is every vertical slice is at the same sync or timestamp. If you see like one component is just all on the left or all on the right, you can generally tell that those timestamps weren't written correctly. So this is just a gut check, right? So with all that, we're going to go forward with calibration. You can see the actual calibration itself took 30 seconds. So it took 30 seconds to calibrate this whole data set, and like 18 minutes to bring in all the data with rendering. So turn off rendering, and you'll probably get that down to like 6 or 8. And then this whole data set would take 7 minutes to calibrate, which is great. That's really fast. You can see after that our calibration results. Here are the bin reprojection errors. EUCM seems to do really well in the middle, but for some reason, the edges of our calibration are a little off. These aren't horrible. This is less than a pixel, but it's not great. So there's maybe another camera model that fits this a little better that we could use. A couple that come to mind for this wide field of view kind of lens are double sphere, Omni. Omni might be a little bit too strong, but could be. We also offer a power law model that fits a power curve to the lens itself. So all of these are low parameter, high descriptor models that we would recommend for this. And then here, very interesting, we take every stereo pair in the data set and we will rectify it for you. So a stereo pair is not defined by looking in the same direction with a certain baseline. It's actually any camera that shares an observation with another camera. So stereo pairs are just any two cameras that see the same thing at any time. And we will rectify that in MetriCal and show you the stereo pair rectification error that this would produce if you used this calibration in the wild for stereo depth, for instance. And you can see this is actually looking really good. We're getting RMSE of 0.7 pixels per detected features. And you can see the histogram of that bin rectified error here. If you were to use any of these two cameras to create depth, odds are that depth would be pretty good. Obviously, this could be more accurate, but for cameras that aren't even really designed to be creating depth, these are pretty solid numbers and give you a good feel for the quality of your extrinsics, even without going to the extrinsics error, which is here. So we have component extrinsics errors between every component that shares an extrinsic. Blue is best, green is fine. You can see all of these are actually really, really good metrics. Again, another quality check on the calibration. Observed camera range of motion here describes the angles that the camera shared with all objects. This is only important. This is very important in camera calibration. You're going to want as many angles as possible, many variations of angles, because what constrains a calibration is not necessarily seeing the board, but how the board is seen. We're going to want variance in depth, and we're going to want variance in the angles, or sorry, the twist in Z. So with those, we can constrain F, CX, and CY pretty well. You can see the observed camera range of motion is really high here, nearly 100 degrees in every axis, so we're totally good. Here are camera summary statistics. So that's just taking the above reprojection errors and kind of crunching them into your traditional one number reprojection. This is looking fine. This is fine. But we did get a data diagnostic. So at the end of every calibration, you're going to get MetriCal will produce a series of high, medium, and low data diagnostics, or high, medium, and low risk data diagnostics. If MetriCal produces any high risk data diagnostics, it will cut off your calibration. It won't count that calibration. And it will tell you what you need to improve to make that calibration more guaranteed. So even if you get a number, the data might not even be of a certain quality where the calibration would make sense, right? And so we want to guard against that. Here we're seeing that my medium risk coverage is poor camera features, poor camera feature coverage. We only got 57% of the frame for the left fisheye camera, 67% for the front fisheye camera. Generally, we're going to want over 75%. And you can see that pretty easily up here, right? We have so many zeros of areas in the frame that just didn't have any detections. Now, it could be that you actually did capture detections at these, but they were just filtered out by the motion filter, in which case you would just increase the motion filter and allow in more data into the calibration. That could be, you could be too harsh, but it also could be that you just forgot to get that section of the camera, right? So again, we make this a medium risk diagnostic so that in the case you did this on purpose, it's still allowed, but you should be aware that, maybe things would be a little better. And here at the very end, you get the actual calibrated plex. These are your calibration numbers. We, of course, use the distortion model EUCM. Our alpha and beta parameters are here. FX, CX, CY are here. These look pretty self-consistent, which makes sense because they're all the same camera model. And then here are our calibrated extrinsics. So it's to note the 2 component for all these are origin. We use the 2x from y convention when talking about extrinsics. And so from the origin of the back fisheye camera, you can see we get these translation and rotation values. All right, so we did it. That was all of it. But we can do one more thing. So we went through all that. Let's comment out our first 2 commands that we just ran, and let's actually display what that calibration would look like when applied. Oh yeah, no, this whole thing was for LNS, right? And LNS was so easy, I didn't even cover it. Here it is. So there's our odometry, and there it is to our fisheye camera facing the back. So with that, you can construct a whole chain of connections between every component, and you've fully registered your odometry to all your cameras. It was that easy. Like, it was so easy, I even forgot to cover it. But let's run, while rerun's still up, let's run this rectified data set, huh? Let's see. So we had that, if you remember, we had these wide field of view images that we wanted to see. But now let's look at what our calibration actually produced. Boop. Here we go. So here's rerun. Let's refresh. Always refresh if you're going between views. So we're rendering the calibration onto the data set, and you can see these lines look pretty darn straight. EUCM could be better. Of course, we saw these errors, we saw some orange and green errors, but really, this looks fine. I would use this in production probably. Here's our Plex, and you can see if we click on this guy, this is our odometry source. So this is the chassis. If you could see the car, this would make sense. This is kind of right in the middle of the chassis. And then here are 4 cameras, 1, 2, 3, 4. And if we zoom out, yeah, that looks about right. This is a pretty solid calibration. And then one other cool thing that MetriCal produces is the object space. So you can see actually here, you can see there we go, 2 boards. And how we also solved for their position relative to the rest of the calibration. So this is what I mean to say when you can just use as many boards as you like. MetriCal will solve for the position of those boards and present to you the solution. And here we go. Just as we said, here they are aligned up. So there you go. We can feel pretty confident in this, both qualitatively and quantitatively, that this calibration is looking really solid. There we go. And that was it. So that entire flow was just one freaking script that I could have written in 3 minutes, maybe, and that I could have ran in 8 had I not been rendering everything. That's my bad. But it was very illustrative in what we can expect from Calibrate, what we can expect from Init, and how all these things interact to produce a great calibration. All right, so with that, go into Q&A. Ilya, you had one question. Do you support non-parametric models based on any other dense models? Dun, dun, dun. Let's see. Um, Currently, we don't. We use, so here's what we got. I'll actually show you. Here we go. Here are all of our parents' models. So we use, oh, I'll actually share my screen because this is relevant. Dun, dun, dun. So I'm assuming you're talking about camera models. Our current camera models are as shown in our documentation. So we have no distortion, which is just pinpoint, or pinhole rather, just FCXUI. We have the two OpenCV or three OpenCV models and the documentation references for them. We have two inverse models, which we call pinhole Brown-Conrady, pinhole Canala-Brandt. So inverse, also known as correcting, is finding the camera ray that is created when the extrinsics are applied to the image. So generally modeling, you would put the object point or go from image to object point. But here we go to object point to image. Go the other way around. So this is good for correcting an image really quickly. But to be honest, very few of our users use it because they're generally looking for something a little bit more optimized for SLAM, for instance. In which case, they're probably going to be using EUCM, Enhanced Unified or Double Sphere. We've just also, I would just say just, at the beginning of the year, we introduced omnidirectional, which is a spherical omnidirectional model. And we've also designed this model called Power Law, which actually we didn't see in any publication, but was asked for by a user. So if you're going to your question, if you're looking for a specific camera model or an idea that you would like to see in MetriCal, this is kind of our bread and butter. This is I wouldn't say it's easy to do, but we've done it a few times. So if you want something specific that fits your models or your research, just let us know, and then we'd be happy to implement it and try it out, certainly. But all of these are in our documentation. All the mathematics is there as well. So if you want to understand how to actually apply these things, or you're looking for a new camera model, we've tried to document them as well as we can. And if you do have any questions, again, just email us for sure. Actually, let me wrap this up. So we're running out of time, but thank you for letting me go through my demo. There are a few resources that I'll leave you with today. First and foremost is the MetriCal documentation. Here's the docs. We've written a lot of docs. We're not proud of we are proud of our docs, but we're always looking to improve them. So if you see something again, message us at info@tangramvision.com. The MetriCal user hub is hub.tangramvision.com. If you want to sign up for an R&D or growth license, you can just do that on your own. You don't have to go through sales. Go to the hub, sign up. It's ready to go. Otherwise, MetriCal does have a free tier. Again, it's just generating data and generating reports. It won't give you calibration numbers, but it'll give you everything else so that you can understand the value. And then, of course, our Tangram Vision website, tangramvision.com. Whew. All right, I did a lot of talking. Next week, if you want to have an actual discussion with me and not just hear me lecture, it will be MetriCal, or not MetriCal, Tangram Vision office hours. That'll just be me hanging out for an hour, talking to whoever goes. So if you have something that's on your mind about calibration, cameras, modalities that we're bringing in, or just, your own research that you'd want to rubber duck with the rest of the team, I'll be there. We'll be there. And we're happy to talk. That is not a sales pitch. Of course, if we can sell you something, we will. But in general, we're just looking to understand what you're doing and, just be a helpful hand. So, looking forward to it. thank you all for joining, and I'll talk to you soon. Peace out.